Hello and welcome to AP Statistics Office Hours with Daren Starnes. My name is Curtis Brown and I'll be your host this evening. I'm certainly happy that you guys have joined us. Daren, thank you once again for joining us this evening. I know we've got a great set of things lined up. I'm going to just make a couple of references before we get started. We have a bulletin board blog post on the TI education.ti.com website where all of the information from all the previous office hours are located. You can go and check those out. There's links to each of the office hours on our YouTube channel, as well as the presentations for each of the sessions. We'll post tonight's presentation shortly after this session this evening, and we'll make sure that link is in the chat box for you here. I also just want to, again, thank you, Daren, for this year. It's been a good year, and hopefully we'll be able to do this again in the coming school year. But I guess for now, let's go ahead and get started.
Let's do it. Thanks, Curtis. It's been a pleasure working with you this year, and glad to be here for the grand finale of AP Statistics Office Hours. I know it's been a year to forget or remember for everybody, so I'm really glad we were still able to provide some insights this year while people are struggling through with teaching during the pandemic. I'm going to go ahead and share my screen, just make sure everything's working okay. How's it look there, Curtis?
Looks great, Daren.
All right.
Looks great.
Let's get into the plan for tonight. The goal tonight is to show you how we can deal with topics in units 7 and 9 of the AP Statistics Course and Exam Description, or CED, with both the TI-83-84 and the TI-Nspire. Unit 7 is inference for quantitative data, means, and unit 9 is inference for quantitative data, slopes. So it's two very different types of inference. One is just one variable, and the other is two variables, both quantitative in the case of inference about slope. And as always, we want to share some real world examples that'll help connect the concepts in these two units. But along the way, we thought it would be helpful for Curtis to review how we get the data from a CSV file into the calculators, because that's something we did in the very first session. But I know I sent him a new data set this time for this session, and he's a wizard at getting the data transferred in. So we thought it would be worthwhile seeing that one more time. And then we want to answer your questions. If you have a question, please feel free to stick it in the chat, and we will do our best to respond to it. If we have a little time at the end, we'll open up for questions, but if you have one, please just put it in there, and we'll keep our eyes on it. So let me tell you the scenario, and then Curtis is going to shortly show you about the data transfer. So if you were with us for session 1, there was a story going about my wife and my return to Yellowstone National Park to see Old Faithful without our kids. We had done a similar trip about 25 years earlier, and it is always a pleasure when you can see Old Faithful erupt. It's pretty consistent, fairly predictable, but we were curious about how things might have changed since we had gone in the 1990s. So ironically, when we pulled into the parking lot, the same thing happened to us that did when we took the kids in the 1990s. The geyser had just erupted and all the people were coming back to their cars and the buses when we pulled in. So we were in that moment again of like, how long should it be until the next eruption? Should we maybe go do something else, get a coffee, or go hike around somewhere before the geyser erupts? So you know me, I decided we'd look at some data. So the first problem we're going to talk about tonight is this scenario of how long will we have to wait for an eruption of Old Faithful. Now, I collected some data before the trip because this had come up 25 years prior when the kids were with us, and I took a random sample of 80 Old Faithful eruptions in the months January through August 2019 before we actually went to Yellowstone. So I had that data set, and I managed to type them all in, and then decided I would send them off to Curtis. So the problem we'll be doing shortly after we figure out how to get all that data into the calculator is we're going to construct and interpret a 90% confidence interval for the mean wait time for the corresponding population of Old Faithful eruption. Curtis.
All right, so I'm going to go ahead and I will share my screen. Daren, let me know.
Gotcha.
You can see. All right, perfect. So what I've got open here is I have Daren's file that he sent me, Old Faithful Finale 2019. And he's got 3 unnamed lists here. One of them with the duration in A. The second one in B is the interval between durations. And then we'll talk about column C here after a little while here. I don't want to spoil too much. So what we're interested here in the first problem anyway, in this first question scenario is really just those first 2 columns. And the question is, how do I get this information into this connected TI-84 Plus on my calculator, so on my computer? So I have TI Connect CE open. It's the transfer program. It's how you connect your calculator to the computer. So I have mine plugged in here, and the second icon down is the Calculator Explorer, and you'll see all kinds of things here on my list here of things that are in my calculator already. And what I'm going to do is I'm going to look to add some content I'm going to look to take an action. Adding content wouldn't help me here. I'm going to import data from a CSV file into a list or matrix. And so I'm going to choose that option, and I will look for, and lo and behold, I have Old Faithful Finale here, right here close, so I can open that up. I just wanted this here so you guys would know what was in it. And I'm going to choose from the lists, and I'm going to just put in 2. Now, the way this works, it goes from the left, from A out to up to 6 different lists can be pulled in. So you can go from A to, what is that, F, I suppose, so whatever those columns are. You can choose all of those. I'm just going to do the first 2. I can't pick which 2. They just are going to be A and B. And I'm going to collect that. Now, I could just drop them into list 1 and list 2. Totally fine. That's probably what most of you will do. But I also want to just demonstrate quickly that you can custom name your lists so you don't lose data later on when you're putting things in list 1 and list 3 through list 6 and then deleting them out and clearing them. You don't want to accidentally delete your data completely from here. So I'm going to call these, I don't know, Old Faithful duration might be a good one. So I'll just call it OF dir and say done for the first one. And then I'll do the same thing for custom named list. I might use OF interval for the second one and hit done. And then that's it. And my data gets transferred. You saw that go pretty fast. Now my calculator, if you look down here, I have a list called OF dir and another one called OF int. And that's the data that is on that calculator. I could prove it to you, but I think you guys probably believe me. I will stop sharing, Daren, because I think we have a lot to go through, and I want to make sure that we can get through that. And I also want to make sure that we can talk to the Nspire quickly. So I've got some slides in here on, I think they're the next couple slides here. There we go. So if I wanted to go into Smart View from that case, what I would do is I might take my calculator that I have those 2 lists, and you can see that in the left-hand side of your screen there. If I have those 2 lists in my calculator, I can save them off to my computer. You'll see which icon is highlighted up there. It's the one with the arrow pointing into the computer, sends connected content to a computer. And then once I've sent it to my computer, then I can add content from my computer in Smart View and select those lists, and then they'll just get brought into my 84 Smart View. So that's a quick way to get that into Smart View. You can do the same thing in Nspire. You can import things, but I think it's much faster to just copy and paste, which is really nice. So I can just copy from that list over there in my CSV file and just paste them in there. And then on the next page, you'll see that you can name the lists after you've pasted that information in. So you can do something like that. All right, Daren, I think that's the quickest way to get this stuff in.
That's great, Curtis, and it's a very useful skill. Trust me, I had no fun typing in that whole list of 80 values, and I knew that Curtis would come up with a shortcut for me. So I appreciate that. So here were the data on wait times until the next eruption from that random sample of 80 eruptions. And the problem we're going to tackle is to construct and interpret a 90% confidence interval for the mean wait time in the corresponding population of Old Faithful eruptions. So I'll do a little bit of AP stats type setup, thinking that the AP exam is going to come upon us pretty soon. So first thing I like my students to do is talk about what it is they're about to do. So if they were doing a hypothesis test, they would state their hypotheses. You'll see an example of that later. But for a confidence interval, I just want them to sort of repeat what it is they're going to construct. So a 90% CI for mu equals the mean wait time in the population of Old Faithful eruptions in January through August 2019. Students have a really hard time defining the parameter that they're doing inference about. So it's a good thing to give your students practice with because I'm pretty sure they're going to be asked to demonstrate that skill at least once on this year's exam. The type of inference we'd like to be able to do is a one sample T interval for a mean, T interval because we don't know the population's standard deviation of wait times. So we're going to use the sample standard deviation to estimate that unknown sigma. And because of that, we have to use, we would like to use a T interval. Of course, you all know the punchline. We can only use the T interval if the conditions are met. Fortunately, I really did take a random sample of 80 eruptions. It wasn't a lot of fun. The data format on the website I sampled from was pretty unpleasant. So I actually cleaned the data set to get it into the form that you saw earlier. And then because we're sampling without replacement from a finite population of all the eruptions during those months, I just wanted to confirm that 80 is less than or equal to 10% of all those eruptions in those months. And that is definitely true. Old Faithful erupts an amazing number of times. It goes off about every 90 or so minutes. So you can do the mental math on that to convince yourself over the August back through January period.
A lot of eruptions.
Yeah, it's pretty reliable. The other thing we need to check is that we are going to have a sampling distribution of the mean that's approximately normal. And in this case, the sample size is large enough that we're good to go. So all the conditions are met. None of this involves using my calculator yet, but we're about to. So like Curtis, I needed to come up with some names that I would remember later. And I used the name OFW19 for Old Faithful wait time in 19, because I already had the data in my calculator from 95 when I went the previous time. So in my calculator, I should find that in list 1. And then in just a second, I'm going to go over to the calculator and do some computation. But I want to remind you on the formula sheet for the AP exam, students have this generic representation of a confidence interval. And so they need the statistic from the sample, they need the critical value from the t-distribution, and they need the standard error of the statistic. So if they're going to do it that way, here's the formula, x bar plus or minus t star times sx over the square root of n. But I'm just going to show you one way on the calculator here. If you want your students to use that formula, then you can just have them do 1-var stats. And then they can get x bar and they can get sx directly off of there. Now you're going to need to get the t critical value for 90% confidence. So picture 90% of the area in the middle of the t-distribution curve between like t star and negative t star. That means there's 5% on each tail. And so I did an inverse t with an area of 0.95 to the left of that place. I could have also done an inverse t with 0.05 to the left of that place to find the left-sided value of negative t star.
That's a really important skill, by the way, Daren. I think that is one of the biggest tricky things out there in thinking about what portion of the distribution do I need to have. Yeah.
A lot of students will do inverse t 0.9 because it says 90% confidence interval.
Right.
And that's not the right thing to do. It's the area to the left of wherever you're trying to locate.
Right.
So with those two screens, we can plug into ye old-fashioned formula. And okay, I cheated a little bit here. I didn't I didn't feel like mashing all the buttons. So I showed you that we can actually get, by taking this answer times Sx over the square root of n, those were stored when I did the 1var stats, and I got the margin of error, and then stored it into m, so you would know it was margin of error. And then I just did the sample mean minus the margin of error and the sample mean plus the margin of error to get my endpoints.
Very nice.
So yeah, I was playing around with the calculator a little bit. I didn't need to do all that, but it was kind of fun.
Well, that's a good way to remember that you can store things, and that we have variables that are already computed. Anytime you do 1var stats, it computes a great number of things that are useful for other calculations.
And then you don't have round off error.
Right.
A lot of times the kids will worry about how many decimal places to round off to, and really you shouldn't round off in the middle of your calculation. The calculus people would really get upset with us for the things we do in AP statistics. We're a little loosey-goosey with rounding and decimal places, but this way I feel pretty confident about my answer to 3 decimal places. Sorry, I had to do that.
I see what you did there.
Had to do that. All right, so that's one option, right? That's maybe not the option every student should take, but it's a legitimate option. Plenty of students can go through the formula and use the technology, or even the old-fashioned tables. They could still use the tables to get the t-critical value here, except they'd have a little problem because the degrees of freedom is 79, and the table doesn't have that. So technology really is better. I know.
Yes, in this case, yeah.
I know that's shocking to people here in the 21st century, but those tables were made a long time ago. And although those of us who are old enough to remember using them really love them, I'm kind of fascinated by the technology. So let's get real here. I mean, what we really should do is just go to like stat and arrow over to tests, and then find one that says t interval. And then all we have to do is make sure that we use the correct list. Well, I showed you I stored it into list 1, and my confidence level is 0.9 or 90%. And I'll calculate and just make sure I get what I got before. Like, I'm sorry, but if a kid's trying to be sure they get the right calculation done on the exam where they've put raw data into their calculator, this seems like a pretty good bet.
Yeah.
As long as they type carefully. Fortunately, the AP exam is not going to give them 80 values that have 3 decimal places in some of the values. That's just not going to happen. So I would actually recommend for some of your kids that they do their intervals this way. And I'm going to make the same recommendation when we do a significance test later, because their calculation skills, when you do this kind of stuff, just aren't that reliable. Now, they can't duck the issue completely, because if the test writers want to put a multiple choice that addresses the calculational nature of the formula, they can do that, and that will expose the kids who have trouble with the formula. So I feel good making that recommendation to try to get your kids 1 point, or at least hope to get your kids 1 point if they have raw data to enter on the exam.
Yeah, I think that's a really good strategy, using the built-in inference tests and intervals. Yeah. And
then, of course, we need to interpret our interval. So we're 90% confident that the mean wait time in this population of January to August 2019 Old Faithful eruptions is somewhere between 93.378 and 95.022 minutes. But I decided I didn't want to stop there. A lot of AP exam free response questions that have confidence intervals have some kind of follow-up part or parts. And so I wanted to think about how to follow up on this. Warning, this first part is a little bit of a curveball. So the National Park Service actually predicts on their website that the wait time until the next eruption of Old Faithful will be 94 minutes plus or minus 10 minutes. That's how they do it. So according to the National Park website, this interval is based on a 90% confidence level. Please note, that is not the confidence interval I just came up with from my random sample of eruptions.
Agreed.
Actually, I'll just say, well, no, I won't say it yet. So following a randomly selected eruption of Old Faithful, is it believable that the wait time until the next eruption will be 100 minutes? So we're just basing that on this interval of wait time until the next eruption, 94 plus or minus 10. Well, 100's in there. That goes from 84 to 104. 100 minutes is believable for the wait time until the next eruption. Now, just hold on to that thought and let's look at the final part. Is it believable that the average wait time between Old Faithful eruptions in January through August 2019 was 100 minutes? Note the difference in the questions. Part B is about the time until the eruption of the next occurrence of Old Faithful. Part C is about the average wait time for the entire population of eruptions over those months. That's not the same thing. The one in Part B is called a prediction interval for a future value, or just a prediction interval. C is a confidence interval for a mean. So we need to look back at our interval that we got and see if 100 is in there. It's not. 100 is not a believable value for the average wait time for all the population of Old Faithful eruptions.
And if I was a student who typed in all 80 of those values, I probably would have a pretty good sense of the answer to part C without having seen that interval.
And I was a little bit mean to put part B in there, but I just couldn't resist because that's what the brochure and the information at the visitor center was telling me. But that's about a prediction of a single future eruption wait time.
No, and that's a great question, and I think that would be a very interesting one, a believable one, maybe even.
Feels a little investigative. Mm-hmm. Has a little bit of an investigative aspect to it, which students will find on our exam as well. All right, so let's move on to the other thing my wife and I really wanted to know, which is if somehow the wait times between Old Faithful eruptions were different in the busier months in the park. So June, July, and August, when more people are on vacation, than in the months with fewer visitors. So that would have been January through May in our time period. So I was able to take the random sample that you saw earlier and split it out based on which month it came from. And for the busier months, here are the data. And for the quieter months, January through May, here are the data. And the question we're going to try to answer in a little bit is, do these data provide convincing evidence at the 0.05 significance level of a difference in the mean wait time for a subsequent Old Faithful eruption in the busier and quieter months of 2019? Maybe there's a difference. Maybe it's a performer. It performs more in the summer months. Maybe there's something seasonal about it in the way that the pipes get frozen or unfrozen. I don't know. Well, Curtis, what about that third column?
So, so that third column that Daren showed just a minute ago was the way that he categorized busy months and not so busy months, and using a 1 for the one was the quieter months, correct? And then the busier months was a 2. And so one way you can do that is go down and break your CSV file into 2 chunks, kind of copy and paste, or cut rather, and paste that into a new column. And keep in mind, you don't want to keep those 1s and 2s because on the 84, what you really need to create are two sets of associated durations and intervals. And so you want to create that. And so I've done that over here on the left. Then the process would be the same thing as you navigate through to the right. Now, we also talked about the ability for Nspire in this case to do something maybe a little bit more, which is really kind of cool. So in this case, 84, we can create this, we can go back and we can do the computations that Daren's going to take us through here in just a moment. But on Nspire, we've got an ability to plot these data side by side, or in this case, in a stacked sort of format. And using the season, quiet or busy, and I went ahead and I replaced the 1s and 2s with quiet and busy, taking advantage of the fact that in Nspire, I can give it a categorical string name. And then I can use that name. If you'll look on the left here, or on the right picture here, you'll see that I've got season graphed on the y-axis there. What you have to do is you have to go in and plot that season on the y-axis and then force that y-axis to be a categorical variable. And that's how this splits into the two chunks. And it'll split that from quiet and busy. You may get a little notification once you first try that. It may assume that you have a numerical data set since your duration was numerical. It's going to assume that you have a numerical data set and you'll say invalid or something like that. So you have to change that y value or that y variable. You have to change it to a categorical variable, force it to be a categorical variable. Then you get these dot plots where you can make a box plot or whatever you wanted to do at that point.
What's really cool about this is now we can take a quick look at the parallel dot plots and just observe that it's not clear to me that there's much difference between the busy season and the quiet season. Just visually, I'm not seeing the busy dot plot shifted way to the right and the duration dot plot shifted way to the left. There's a lot of overlap here, and maybe the center of the busy distribution is a little bit higher, but I can't tell for sure. So just guessing omnisciently, I'm not seeing statistically significant difference here, but I wanted to at least throw out the problem, and this is what the data show us, and then we can go through the steps. That was great, Curtis. Thank you.
Yes, sir.
So you've seen the data, and I've kind of given away the spoiler alert there. So if we're going to do a hypothesis test, we need to start by stating our hypotheses. So I used B for busy or Q for quiet. And so our alternative just said, is there a difference in the mean wait time for a subsequent Old Faithful eruption? I might have led you to believe I thought it would be more common to be one way than the other, but that's not what the question says. The question says, is there convincing evidence of a difference? So that could be busier being bigger or quiet being bigger, either one. So we have a not equal to for our alternative. And then we need to define our parameters. Mu sub B is the mean wait time for subsequent Old Faithful eruption in the busier months, and mu sub Q is the mean wait time for subsequent Old Faithful eruption in quieter months. We'll state our alpha level, just make sure we noticed it. And once again, I've shown you that I've put two separate lists in here, OFB for the busier months, OFQ for the quieter months. That way I can keep it straight when we want to go in there and maybe do some calculations. But don't worry, I'll bore you with some details first. In this case, we would really like to do a 2-sample t-test for a difference in means. Completely coincidentally, the same number of eruptions occurred in the busier months as in the quieter months when I took the random sample of 80. There were 40 and 40. I didn't force it to be that way, it just came out that way. So that was kind of unexpected luck. Now, we would need, therefore, to be able to view these two sets of data as separate random samples of 40 Old Faithful eruptions from busier months and quieter months. And even though I split the original random sample in two, that's effectively what we have here. We have independent random samples from busier months and quieter months, just created in kind of an unusual way. Again, we need to check the 10% condition that 40 is less than or equal to 10% of all the eruptions in the busier months. And the same thing for the, whoop, got a typo there. Should have said quieter months. I did busier months twice. Oops.
That's okay.
Normal large sample, we have 40 for each group. So that takes care of large sample size. And I'm just reminding you that the data are sitting in there waiting for our calculation. So you can probably guess what I'm going to do here first is maybe we want to have our kids work through that formula. And there's a punchline here. So we do the 1var stats on each of the two lists, the quieter and the busier. And we plug in the corresponding values for the busier month, which was 94.55, and the quieter month, which was 93.85. Then we grab the standard deviations for each of them, which were really, really similar, scarily similar standard deviations for these two samples.
Wow, yeah.
And then put the standard error here in the denominator. And if you do that, you get negative 0.71 after a lot of very careful typing. And now the punchline comes. The p-value is what? Using what degrees of freedom? Because That is not an easy question at all. So I'm going to make that statement again. I really think, especially for two sample inference problems, most students are much better served to use the technology that they have in front of them. This is not a great option because we're kind of stuck now. We can't come up with the degrees of freedom easily because it's some crazy decimal, and therefore we can't find the p-value easily. Back in the old days, you did crazy things like use the smaller of the two sample sizes minus 1, so 39. But that's really not a good idea. You're going to lose a lot of power for your test.
Sure.
So instead, it seems to me like maybe we should use stat tests. That seemed to work well the last time. So let's go to stat tests. Let's do a two sample t-test. We've got our data in L2 and L3, that's correct. But our alternative hypothesis is two-sided. We're not going to pool, even though the sample standard deviations were darn near identical. We don't pool in the AP Stats course, even when that happens. And we'll calculate what we get. T equals negative 0.71. But we get the bonus of having the p-value there and the degrees of freedom, 77.999995, almost 78. So to me, that seems like a much better choice because you get the t-statistic and you also get the p-value and degrees of freedom. So the p-value is pretty high, 0.48. That's not a very unusual result if the null hypothesis is true. So I think we're ready to officially make the conclusion. No, these data do not provide convincing evidence of a difference in average wait time for subsequent Old Faithful eruptions in busier and quieter months of 2019. Because the p-value of 0.4822 is greater than our alpha level, we fail to reject HO. And I just have the students repeat that sentence, the data do not provide convincing evidence, that I said a moment ago. That's basically just taking the question and turning it into a statement at the end.
Hey, Daren, I do have one question, and
yeah.
I should have probably asked it earlier on, but when you stated that we had two independent random samples of busier and quieter months, how do you justify that? I mean, let's hypothetically say that this was an AP question. How would the student justify that based upon kind of the method that you used? I mean, I gather that they are independent. How do we say that?
I'm sorry you were listening closely and watched me wave hands there, but yeah, it's really unfortunate.
I don't mean to trap you. I feel like this is a place where a student could or would struggle with how would they justify this.
And ideally, the question writers won't put the kids in this situation. They will take separate random samples from the busier months and the quieter months. But this, I wanted to be truthful with you about how I obtained the data and how I split it after the fact. It's quite a common move, and it turns out that it's okay to treat the samples as if they're independent when you do that. And it has happened in the past a couple of times on the AP exam that students were faced with this kind of scenario where the split occurred after a single random sample was taken. So what the students need to address is the fact that there was random sampling. Both the busier and the quieter months were random sampled. The fact that they came out the same number of eruptions for each was a coincidence. That may not have happened. If I do it another time tomorrow, it won't happen, I'm sure. So the students just need to be able to address the fact that random sampling occurred, so therefore we can generalize, and that there was random sampling for both groups.
And because they were randomly sampled, that kind of gives us the idea of this independence between the two.
Well, I wish it were totally that simple, but what I do is lean on people who are like expert statisticians out there, and they say, "Oh, this is done all the time. You guys get so fixated on these really tight conditions in AP statistics. You guys need to lighten up a little bit, because in real research, we would think this was great that you took a random sample. we might have just collected data on 80 eruptions that we could find in a 3-month period and use that as if it were kind of like a random sample.
Kind of representative, and assumed that it was representative. I did get an interesting question early on in here, and I didn't ask it of you, but somebody did ask about maybe the difference between let's see, what was it? Psychological statistics, psychology statistics, and sociology statistics. And I think maybe some of what we're talking about right here actually is some of the difference between those things, right? Is the ability for us to be able to get representative and random samples versus we have to rely on volunteers and things of that nature.
Well, in fact, if you throw in mathematical statisticians, they have their own language that focuses way more on the formulas than we do. So the nice thing about the AP Stats approach is that it's, I mean, it is restrictive in terms of having the students check conditions. And if they go on to further stats courses in whatever discipline, they're going to find the rules getting bent, if not broken, more often. And the researcher's going to wave hands, just like I was doing tonight, and say, well, but based on my 100,000 years of experience and all of my colleagues, we know that that typically represents the data well if we do a convenience sample. Whereas in AP Stats, we would give them the big X and say, no.
we would throw our arms up and say, what do you mean?
You can't do it. I'm sorry.
You can't do convenience sample. It's going to be biased.
Can't do it. All right. Well, I'm excited because the thing that really struck my wife and I, not so much our kids, they were more interested in like the bubbling mud pots and Old Faithful when we took them to Old Faithful. But we were interested in whether the duration of the previous eruption could help predict the wait time until the next eruption. And back in session 1, we looked at this question for 1995. And we found out that there appeared to be some pretty compelling evidence, but we didn't run any kind of inference because we were just doing exploring data.
Right.
Well, now we can do some inference. So these are my 80 randomly selected eruptions, and I want to try to figure out whether there's convincing evidence of a linear relationship between duration and wait time. We'll need to look at the scatter plot and be sure that there really appears to be anything linear going on and not some kind of curvy pattern. But I'm going to ask that we assume the conditions for inference are met. Much as I love doing these webinars and enjoy hanging out with Curtis, that would probably add 30 minutes to our timetable to check the assumptions for inference about the slope. And I know I am certainly hoping and wishing that nothing about conditions for inference appears on the AP exam other than maybe a multiple choice here or there. I hope that kids aren't going to be needing to do that. So we'll cross our fingers.
These conditions for inference with bivariate data get to be a little bit challenging.
Yeah, it's not fun. It's not fun. Yeah. So just let's assume the conditions for inference are met. I'll tell you that I checked them, and then I just said let's assume. So
here.
I've had to add a list 4. This is where I'm going to put my durations because I didn't have those in my calculator before. So I've inputted the durations. I was only focused on wait time in the previous 2 example questions. All right, so we're assuming the conditions are met. If we're going to do a test about whether the data provide convincing evidence of a positive linear relationship, well, the null hypothesis is that there's a horizontal or no linear relationship, that you might as well just guess the average wait time for every eruption, that the duration doesn't help you predict at all. So just guess the average wait time for every single eruption. And that's kind of what the Park Service approach is doing. Like they're doing a prediction interval, not a confidence interval, but they're saying my prediction interval is 94 minutes plus or minus 10 minutes, period, every time. They're not using the wait time of the previous eruption. So I was kind of curious, like if we use the wait time of the previous eruption, the duration of the previous eruption, do we do a better job of predicting the wait time? So I'm curious if there is truly a positive linear relationship or not. So here beta is the slope of the population regression line for predicting wait time from duration of the prior eruption. We use alpha equals 0.05. So we would like to do a t-test for the slope, and I've already said that we're going to assume the conditions are met. This time I'm not going to mess around and go through the exercise again of setting up the formula, trying to run some kind of 2 var stats. It would be 2 var stats this time, recognizing that we may not have all of the things we need for the formula on the formula sheet necessarily from doing that. And quite frankly, if we get this far along on the AP exam this year and we're doing a question about inference for slope, I don't feel like it's going to be one where we're having to grind out complicated formulas. I'm looking in my crystal ball there, but I really don't think so. So I'm going to go over and clear this off and then run the linreg t-test stat calc.
While you're doing that, Daren, I think this would also be a really interesting problem set to develop the concept of R squared. Mm-hmm. and really kind of look at, because the way you phrased that, does looking at the previous duration help me predict, and if so, by how much? That I think that's an interesting discussion that could be done too.
Absolutely, you're exactly right. So let's run the test. L4, remember, was where I put my durations, so that looks good, and L1 is where I had my wait times between eruptions for each of the preceding wait times, for each of the preceding durations. And then my slope, I'm trying to test whether there's convincing evidence of a positive linear relationship. Okay. And just for fun, I'll store the regression equation in Y1. Well, according to the magic of the calculator, got lots of nifty things down there, including Curtis's R squared, which we can come back to. Let's be sure to come back. So the t-statistics looks like it's about 3.4, which is, in the world of t-statistics, pretty big. That's a pretty big number for a standardized statistic. It would be really big in the z-statistic world for doing inference for a proportion, but t of 3.4 is still pretty big. You can see the degrees of freedom is number of data points minus 2, so 78, and the p-value is 5. No, wait. It's not 5. There's some e minus 4 at the end.
Yes.
So
wait a minute.
Believe it or not, students have been known to just write 5. It is not unheard of for students to write that the p-value is 5 and ignore the e negative 4 part. And the exam reader can't really give credit for that. Probability of 5, we feel like there's a misconception that's pretty serious. So it's okay if they write 5 times 10 to the negative 4, or even 5 e negative 4, but 0.0005 is what we're talking about, not 5. So it is important that students see a couple of these where the p-value goes e negative 4 or worse, and don't get thrown off by that. So p-value is pretty small. So according to our criterion of using like a 0.05 alpha level, let's say, the p-value is much, much smaller than that. So we're going to reject our null hypothesis of no linear relationship. And so that means the data do provide convincing evidence of a positive linear relationship between the duration of an old faithful eruption and wait time until the next eruption. So I think what I'd like to do is go back to the calculator and show you the graph of the data, which I have withheld from you this entire time, because I said, I checked the conditions, trust me. You may remember that. And so I just want to show you what the graph would look like. Let me put the correct plot on here. We had L4 for our duration. We had L1 for our corresponding wait time. And let me do a zoom stat on this. And there's our regression line going through. Okay. I didn't want to do the whole problem and not show you the graph. That just seemed like potential fraud to not show you the graph of the data.
I can agree with that.
So we do have some evidence of a positive linear relationship here. In fact, it's statistically convincing evidence. The p-value is 0.0005. But Curtis was kind of delving into, okay, so there is a positive linear relationship. Well, then why doesn't the National Park Service use that they're pretty smart people. They've been monitoring this geyser for countless years and collecting data on the eruption patterns. And the eruption patterns change whenever there's a seismic event, whenever there's an earthquake in the basin, it can change the eruption pattern. So they know about the data. Why aren't they using that regression line to make the predictions instead of just saying, it'll be 94 minutes plus or minus 10 minutes till your next eruption. Thank you very much. Don't care how long the last one was. Doesn't matter. Well, it may have something to do with the fact that they've looked at that R-squared number. So one of the things I could do here is I can plot in the graph, second stat math, I can plot the mean of the wait times, that horizontal line I was referring to earlier. So the wait times are all in list 1. So if I were to graph that on there, we could compare what it would be like to just guess that average wait time after every one of the eruptions. And how much better would the blue line do than the horizontal line at the mean wait time? Well, that's what R-squared tells you. R-squared tells you how large a % reduction you get in the sum of squared prediction errors. Okay, that was complicated. Right. Sum of squared residuals. What % reduction do you get in the sum of squared residuals for using this blue line instead of this red line? How much does the regression line reduce the sum of squared residuals? Well, we had the answer a minute ago, and then I said, oh, we'll come back to it. So let's take a look one more time here. And we should be able to scroll down and see that R-squared number of 0.13 and a correlation of 0.36. So, I mean, that does sort of go along with what we were seeing in the graph. There is a moderately weak positive linear relationship, but it's kind of like a pretty wide blob of points.
It is a pretty, yeah. I was interested. I was curious now, just looking at your picture here, seeing that there are a large number of values sort of close to the mean of your X values. So there's a lot of values kind of in the center there. And so when I'm looking at your red line, and I'd never really thought about it this way before until I've seen your picture here. And the way you kind of described looking at the difference between the blue line and the red line, seeing that there's so many of them. If I went to each individual point, and how much better is the blue line than the red line, it's better for those points that are way far to the left and way far to the right. The blue line is significantly better, maybe. But in the middle there, the blue line feels like it's pretty much exactly the same as the red line. And since so many are in the middle, I think that has something to do with it.
Yeah, and I hit the trace key just to look at a couple of points. So here's the very first data point in the list, the way we entered it. And for that one, the red line is better. That point's closer to the red line than the blue line. So let's move on to the next one. This one is a hard call because it looks like down below that point, the red line and the blue line are just about intersecting. I think the red line might win by just a smidge. Because the blue line is just a little below it there, but that you may disagree with how you're seeing that point. Well, the next one, the blue line wins for sure. I hit down arrow instead of left right. My fault. This one, the blue line wins. That one, the red line seems to win. So, I mean, yeah, we could easily play that game. And what this tells you is that if you square all of those residuals or those prediction errors and add them all up, the total sum of squares from the red line versus the total sum of squares from the blue line, you only get a 13% reduction in the sum of the squares. You don't gain much. And so I think back in the 1990s, the correlation and the R-squared value was much larger. The correlation of the data back in the 1990s that I had earlier in session 1 was somewhere around 0.8. The correlation.
I recalled that.
Yeah, it was quite high. So your R-squared was maybe 0.6 something. Well, then it's worth thinking about how long the previous eruption lasted. but now it's not. So to me, that's a big change in 25 years.
Yeah.
For the Park Service, it's a great thing because it's a lot simpler. Not just 94 plus or minus 10, and they don't have to keep thinking about it. Well, of course, there has to be a part B. So finishing up this problem, we've got a 90% confidence interval for the slope, and it is 3.696 to 10.708. Now, I'll just comment, that seems like a pretty wide interval to me. That we're 90% confident, which is not a particularly high level of confidence. So I stayed with 90% confidence, and the interval could be anywhere from a slope of 3.7, let's say, to 10.7. So for every 1 minute longer the eruption prior lasted, we predict it'll add somewhere between 3.7 and 10.7 minutes of wait time. That's a pretty big difference. 3.7 or 10.7 or somewhere in between.
Yeah.
But the good news is the confidence interval tells you a little bit more about what the believable values for the slope would be. So any of those values in that interval based on the sample data we took would be believable, say 3.7 to 10.7. Now note that they're all positive numbers, which is consistent with the hypothesis test where we rejected the null hypothesis and found convincing evidence that the slope of the population regression line was positive. But the interval gives more information. It gives you the set of all the believable values based on the sample data. And unfortunately, you can see the believable values are all over the place. So because of all that variability that we saw in the graph, there's just too much variability to get a very meaningful estimate when we look at both variables. So the Park Service did their work and they did it well. Curtis, did that trigger any questions off that?
Well, just another interesting thought. So I was thinking about units on this question. So what are those slopes? And then they're minutes per minute, right? Mm-hmm. And that's trying to put that into context of this situation here. The width of that interval certainly does feel wide.
It is wide.
It feels very wide. But then when we start to put it in the context of, okay, we're looking at 3 to 5 minutes or whatever the interval was, I can't remember, for how long each one is. Multiplying those values by 3 and then by 10, it gives me even more perspective for how, I mean, yes, okay, so 7 units wide there, that's, but now when I'm doing the multiplication, that gets huge, really, really wide. Mm-hmm. And that interval seems virtually
useless.
Well,
I think the Park Service would say much the same. So for me, it was interesting to find out that although Old Faithful's still pretty faithful, it's mm-hmm. not faithful in the same way it was back in 1995.
Yeah, the definition of faithful has changed.
There's greater variability. And the mm-hmm. other thing I've learned is that back in 1995, the Park Service focused more on whether the duration of an eruption was short or long. Mm. It was a much more bimodal distribution of eruption durations. And sure. So they would make their prediction based on whether the duration of the eruption was, say, closer to 3 minutes or closer to 5 minutes.
Okay.
There was more of a clear bimodal situation than we see now. Now, there are very, very, very few short eruptions, and almost all of them are in this interval that you see here. Wow.
Well, that's very interesting. That's cool. That's a very, very cool problem.
I'm glad you liked it. It sort of feels like we've put Old Faithful to rest, at least for the next 25 years, or until something wild happens there. Interesting story. It may be the case that the steamboat geyser in Yellowstone has suddenly started erupting again after a period of dormancy. So maybe that'll be the next one that we go try to predict. If it's
that could be a fun set of problems. That's awesome.
I'd have to go back and do research.
Yeah, for sure. Well, we've got the handout and the slides. We will post those at the website that you see there. We'll also put that link again into the chat box. Make sure that you guys can get there. If you have questions, please put them in the chat. We'll be looking for those in the next while. We can respond to those if you would be interested in getting our responses to those questions. I think that's really good. Otherwise, good luck this coming year in the AP statistics tests. I know those exams are coming up very, very quickly. And so faster than anybody wants to admit. So I want to just wish you luck on that. And please refer back to all of the previous YouTube live events that Daren and I have done together this year. And Daren, I look forward to an opportunity. Hopefully we could do this again beginning of next year.
Yeah, that would be great. We'll promise not to Old Faithful you next year. We'll have something new. I had to do it 25 years later, but something new and exciting will happen between now and then. Hopefully, including people getting vaccinated. Yes, for sure. All right. Well, Daren, I certainly appreciate it. We've certainly had a good time, and I guess we'll sign off with that. So good night, and we'll see you next time.